Hey students, this is lesson 6-9, proofs using coordinate geometry. We're going to learn how to prove theorems using figures in a coordinate plane. In lesson 6-8, we learned how to write coordinates. So now we're going to put that to use and actually prove some things. Go ahead and try the review. Check back with your answers. All right, we're going to use coordinate geometry to prove that the diagonals of a rhombus with vertices R at 0, B, H at A0, M at 0, negative B, and B at negative A0 are perpendicular. So we're given this rhombus. We created the vertices, and those are just kind of generic vertices. So remember that B could represent any value, A could represent any value, so this could be any rhombus. And we're going to prove that the diagonals are perpendicular, and that is that our segment RM is perpendicular to BH. Now the way we're going to go about that, this is our plan. We're going to use slopes, and the fact that we know that vertical lines, which appears to be what RM is, and horizontal lines, which is what appears BH is, we know that that any vertical line is perpendicular to any horizontal line, and we can use slopes to show that they're vertical lines. Remember, all vertical lines will have an undefined slope, and all horizontal lines will have a zero slope. So we're going to use the slope formula. All right. So I'm going to just skip a little bit here so I don't have to write everything. But first of all, our first step is just to show what we're given. So that's given. And our next step would be to use those coordinates to create slopes for our diagonals. So the slope of RM is equal to, remember the slope coordinate, slope formula, subtract the y-coordinate. So R and M, we would be subtracting B and negative B. And then subtract the x-coordinates, which are 0 and 0. And we end up with negative 2b divided by 0. And anything divided by 0 is undefined. And then we can find the slope of the other diagonal, which is BH. And that's equal to BH, it's red here. We're going to subtract those two, so we get negative A minus A. Those are the x-coordinates, those need to be on the bottom when we're using the slope formula. So negative A minus A on the bottom. And then on the top, we're going to take the y-coordinates and subtract those 0 minus 0. And that gives us 0 over negative 2A, which is equal to 0, because 0 divided by anything is 0. So RM has an undefined slope, BH has a slope of 0. So we can now say that RM is a vertical segment. And BH is horizontal. And our reasons are as follows. All vertical lines or segments have undefined slope. Let's say have undefined slopes. And all horizontal lines have zero slope. And so we can now say that RM, segment RM, is perpendicular to segment BH. And that's because we learned earlier in the year that all vertical lines on a coordinate plane are perpendicular to all horizontal lines. And we needed that because our normal method for showing two lines are perpendicular, that they're opposite reciprocals or their product is -1. That doesn't work when you have zero slope for one of them. All right. Try problem 1 here. I think I'm going to go through this with you, just because it's a little bit confusing, I think. So what we're trying to do is prove that the midpoint of the hypotenuse of right triangles is equidistant from the three vertices. And to do that, we have to show that three distances are the same. What we're going to talk about here is what coordinates are best to use. And so we're going to just analyze which is a better set of coordinates here to use 0, 0, 0, 2b, 2a, 0, or to use 0, 0, 0b, and a, 0, and just see what happens when we do that. So on the first one, we're going to label our coordinates with just b and a. So the distance on the x-axis is a, and the distance on the y-axis is b. That's b. Okay. The second one, we're going to call them those same distances, 2b and 2a. So this will be 0 there, and this will be 2a there. All right, and then we're going to use the midpoint formula with each and just see what happens here. So for the first one, if we use a0 to find m, we have to use the midpoint formula, which is to add the x coordinates together, which in this case would be a plus 0, and then divide it by 2. Here's where I am right now. And then we have to add the y coordinates together, which are b and 0, divide that by 2. And when we do that, we get a divided by 2 and b divided by 2, which doesn't seem too bad. But on the second triangle, when we use 2a and 2b for our horizontal and vertical distances, we get to do 2a plus 0 and 0 plus 2b divided by 2, and that gives us just AB for our midpoint. Now, in order to prove the theorem, we want to show that this distance here, and this distance here are all the same. And we're going to use the distance formula to do that. And now check out what happens when we use the distance formula on this first triangle. Now remember, we now know that m is a divided by 2 and b divided by 2. So that's our midpoint. So now to find EM, we're going to use the distance formula, which we need to take we need to subtract the x coordinates. So from E to M, that would be 0 and a over 2. So 0 minus a over 2, or a over 2 minus 0, however you want to do that. When we're going to square them, it doesn't matter which way you subtract them. So I'll just do that. A over 2 minus 0 plus b minus b over 2 squared when I subtract the y coordinates. Now check out what happens here. We get a over 2 minus 0 is the same as a over 2, and when we square that, we get a squared over 4 plus, and now with these b's here, here's what I'm talking about. We actually have 1b minus 1/2 b, which gives me 1/2 b. And when I square that, I end up with b squared over when I square that, I end up with b squared over 4 again. So Anyway, and I mean, we can work with that, and we could also show that FM and OM are going to end up with the same expression for the distance, that one there. But watch what happens when we use the other set of coordinates. So for EM, now I'm talking about this triangle right here that I'm using. And for EM, we have to subtract. Now remember, I just have AB for my midpoint here. So we're going to do 0 minus A, or A minus 0, and 2B minus B for my expressions under the square root. So A minus 0 squared, and then 2B minus B squared. And when I do that, I end up with A squared plus 2B minus B is just 1B squared, which is a heck of a lot easier and a lot faster to find. And I'll just do one more just to show you that it is indeed the same distance. Let's do FM. So we're going to do 2A and A, and then 0 and B for the y coordinates. So square root of 2A minus A squared plus B minus 0 squared. And again, 2A minus A is 1A squared. And B minus 0 is B squared. And so we get exactly the same thing. Now, to finish this proof, we would have to also show that OM is A squared plus B squared, but I think we can see that it will be. And so we can see that the easier set of coordinates to use when we're dealing with the midpoint is to double, to use 2A and 2B as our distances on the x-axis and the y-axis. That way, when we're finding the midpoint, taking half of something already doubled, and we end up with a lot nicer coordinates. All right. So we're going to write a coordinate proof here to show that the midpoints of the sides of an equilateral triangle form another equilateral triangle. To do that, we need to find, again, coordinates of the midpoint. They're shown on the graph here. It says ABC is an equilateral triangle with coordinates A at 0, 0. So put that in there. B is 4A, 0. And it says C is 2A. And then it says it's equal to 2 times the square root of 3A. And I don't think that's right. And I'll just show you why I don't think that. So this distance from here to here is 4A, and it's an equilateral triangle, so this side is also 4A, and the other side is also 4A. Now, to find that distance up there, the altitude of that triangle, I'm going to use this right triangle. The hypotenuse is 4A, so I'm going to square that. And then, since I have the hypotenuse and I know this short leg here is 2A, so I'm going to subtract 2A squared. And so using A squared plus B squared equals C squared, then I'm going to do the square root of that to get the altitude. I'll call it H for height for right now. And that is 4A times 4A is 16A squared. And then 2A times 2A is 4A squared. And when I subtract that, I get 12A squared. And just simplifying that, I'm going to break this up. That's the same as the square root of 4 times the square root of A squared times the square root of 3. And the square root of 4 is 2. The square root of A squared is A. And the square root of 3 is the only thing I'm left. So the thing they have wrong in here is that this coordinate C, this A should not be under the square root right there. It should be out here with the A, like that. So I'm going to pause right here. It's going to take another video to finish this lesson. And we'll continue shortly.